This is where things get a little more advanced than the probability you've learned in the past, because it's where we're going to start talking about conditional probability. Conditional probability is the probability that something happens or that something will happen. Okay, so the probability that one event occurs given, and this is the big word here, given that another event has already happened. So let's look at this example. Is there a relationship between gender and having allergies? To find out, we use a random sampler at the United States Census at School website to randomly select 40 high school students who completed a survey. This two-way table shows the gender and whether the student has allergies. So we're going to consider the events. Random selected students consider the events that A, the student has allergies, and B, the student is female. Okay, so let's look at a couple of different probabilities here. If I wanted to just find the probability of A, well, that's easy. That's something we've already done. I know that A is that the student has allergies. There are 18 people here who have allergies out of 40 total. So my probability for A is 18 out of 40. Now, if I wanted to say the probability that they have allergies, given that they are female, that's a little different. That totally takes the males out of the equation because I know for a fact that the person I'm going to randomly select is a female. Okay? And I know that I have 23 females. So if I'm already given that they are female, and it is, if you're talking given, A given B can be represented as A given B. The line means given. So allergies given that they are female. Well, I know that I have 23 total females. Out of those 23, 10 of them have allergies. The probability of me picking a person who has allergies given that they are a female is 10 out of 23. If I flip that, what is the probability that I pick a person who is female if I am given the fact that they have allergies? Okay, I know that I have 18 people who have allergies. Okay, that takes these people totally out of it. Out of these 18, 10 of them are female. So that's how we do givens with a two-way table. Basically, you look at the column or the row that you're given, and your probability is the appropriate cell out of your total. So, given that they are female, 10 out of 23 have allergies. So let's do the check your understanding questions on page 314. These are finding the probabilities from a two-way table. The first one wants you to find P of L. So take a second and try and find P of L. That's the probability that they get a grade lower than a B. And if I add 2268 plus 800 plus 588, which are the three numbers found in the table for below B, and I say that that is out of the 10,000 total students that they surveyed, that means that 0.3656 received a grade lower than a B. And if I want to interpret that in context, I say just that. I can say 36.56% of grades are lower than a B. Number 2, it wants me to find the probability that they are an engineering major, okay, or that is an EPS course, given that they had a grade lower than a B. Okay, so since I'm given that they had a grade lower than a B, my total amount would be the below B total. So that's the 2,268 plus the 800 plus the 588. And then I want to know what's the probability that out of these people they are from an EPS course. So that would be 800. Okay, which gives me 800 over 3656, which is 0.219. And then it wants me to find the probability that they have a grade lower than a B, given that they are from an EPS course. Well, that changes my total to all of the people who are in the EPS course. That's 368 plus 432 plus 800. And it is 800 out of that because 800 is the amount that had the grade lower than a B. So that's 800 out of 1600, which is 0.5. Okay, which of these conditional probabilities tells you whether the college EPS students tend to earn lower grades than students in liberal arts and social sciences? Okay, that would be this one. Okay, this gives you the probability of getting a lower grade if you are an engineer. So given that you're an engineer, what's the probability that you're going to get a low grade? So you would want to compare that to the probability of getting a low grade if you were in one of the other majors or taking one of the other classes. So this one is the answer because I'm wanting to compare the probability that I'm getting a low grade given that I'm a certain major. A key factor in probability is independence. And what does it mean for two events to be independent? Well, for us, it means that one occurrence of an event has no effect on whether or not the other one will happen. So if I have events A and B, okay, independence means that the occurrence of one event has no effect on the probability that the other will occur. Okay, there are a couple of different ways that we test for that. One way to test for it is I can see if having a given affects it. So if the probability of A given B, if I'm saying that whether B occurs or not has no effect on A, then this should equal the probability of A whether or not B occurred. Okay? Likewise, same thing. If I'm saying that the probability of A given B would be the same whether B happened or not, then it should also be the probability of A given the complement of B. So if B did not happen. Okay, these are two ways to tell. You can also think about it in the fact of, if I know that B occurs, does that give me any additional information about whether or not A occurs? So basically I'm asking if there's any association between the two. If there's some kind of association between the two, then chances are it is not independent. I can also think about the fact of, like in terms of probability rules, does it change my overall total? For example, anything that you are not replacing would change the independence. For example, if I took out a playing card, that changes the number of playing cards in the deck if I don't replace it, which therefore is going to change the probability because it's going to change the denominator of my fraction. So, replacement gives you an idea. Okay, independence is something we're going to talk about from here through the end of the year. Independence is a really big thing when it comes to using statistics to make predictions about whether or not something will happen, or taking sample data and deciding whether or not it applies to the larger population. So it's a good idea to get a good grasp on what independence means now. And it's basically saying that if one event happens, does it give us any kind of idea about the other? Does it change anything? So this wants to know if the events A and F from our last example are independent. Where A was that they have allergies, and B was an F that they were female. Okay, so basically I want to look and I want to compare. I want to compare the two givens. So first let's look at this given. What is the probability that they have allergies given that they are female? Okay, we've already said that was 10 out of 23. Which, if I change it to a decimal, which is sometimes nice if I think I'm going to have different denominators so that I can compare them, it's 0.435. Okay, if I look at the probability of just having allergies, then that's just, we've already said, was 18 out of 40, which was 0.45. Okay, these probabilities are close. They are really close together. However, they're not equal, so therefore we cannot say that they're independent. Okay? Knowing that a student is female slightly lowers your probability that she will have allergies. So they're not independent. Okay, let's go ahead and look at the check your understanding questions here. The check your understanding on page 317, go ahead and look at those questions. See if you can answer them and then check your answers with me. The answer to the first one would be independent. I already used playing cards as an example. Since I'm putting the card back, I'm not changing anything about the deck. So if there were 4 kings before, there are still 4 kings. So therefore, knowing what the first card was has no effect on what the second one would be. Number 2, they are not independent. Okay, since I know the suit of the first card, then the probability of getting a heart the second time will change depending on what the first card was. If I pull out a card and it's a heart, then that lowers both the number of hearts that I have left and it lowers my overall total. And for any other suit, it also lowers my overall total. So it would change the probability. And number 3, they are independent. Knowing that the chosen person is female does not tell us anything more about whether or not she is right or left-handed. Because overall, 24 out of 28 of the students are right-handed, and overall, 18 out of 21 are right-handed. Okay, so the probability that the students are right-handed is actually equal to the probability that they are right-handed given that they are female, because these would both simplify down to 6/7. Okay, we've talked about two-way tables and Venn diagrams, but another very useful tool for looking at probability is the tree diagram. The tree diagram helps us when we have conditional probability, so when one thing is dependent on another, or when we're, like, for example, looking at several things that happen or several events that we're looking to happen, one right after the other. And the rule that we tend to use in situations like this is called the general multiplication rule. So what the general multiplication rule is the probability that A and remember the upside down, well, I guess it's not an upside down, but the N, it means and, A and B is the probability of A times the probability of B given that A actually happened. Okay, because if A didn't happen, then there is no probability of A and B. It's 0, because remember, and means that they both have to happen. Okay, so, and there is a simplified version of this, but the simplified version requires that A and B be independent. If A and B are independent, then we know that this is just equal to the probability of B, because A didn't affect B happening at all. So if you know that A and B are independent, then you can use this formula to say that just the probability of A times the probability of B. When is it better to use the tree diagram than a two-way table? It's better to use a tree diagram than a two-way table when they are giving you situations where you deal with a lot of givens, or one thing happens right after another, like a sequence of outcomes. Two-way tables are better if you're dealing with categories of things. Tree diagrams are better if I'm saying, for instance, what's the probability that I'm going to flip a coin 3 times? So a succession or a sequence of things. Okay, so let's look at an example. In 2010, the Kaiser Family Foundation released a study about the influence of media in the lives of young people. Okay, so we had 17% of youth that were classified as light media users. 62% were classified as moderate, and 21% were classified as heavy. And of the light users who responded, which is very important because that tells me that these values are something given that they are a light user. 74 described their grades as good, 68 as moderate, and 52 62 of the moderate users. So that tells me that this is blank given moderate. Sorry, I read the problem wrong. And 52% of the heavy users. So that tells me that this is blank giving heavy. And they're all describing their grades as good. So if they're describing their grades as good, then we're just going to call it A, for like being an A student. So what L be that it is, L be that they are a light user of media. MB that they are a moderate user of media, HB that they are a heavy user of media, and we'll let A represent them being a good student, and we'll let N represent them not being a good student. So I need to define all of my events, and you would need to write all that out. And in fact, I'll go ahead and write it out for you, or at least write some of them. You would want to write it like this so that people, graders, and I would know, what all of your events are. So under this I would put M, under that I would put H, etc. So I want to know, according to the study, what percent of young people describe their grades as good. So I have it all split up in all these different percents, but how do I know how they describe their grades? So if I have a student, I know that there are 3 options. Okay, they can either be a light user, a heavy user, or a medium user. And I guess I should put these in kind of the order. So light, moderate, heavy. And in each one, they can either have good grades or not so good grades. They can either have good grades or not so good grades. They can either have good grades or not so good grades. Okay, so while this is not a sequence of events, it is kind of when one thing is dependent on something else. So here, they are telling me 17% of youth were classified as light media users. Okay, that tells me that of these 3.17 were classified as light. Okay, I know that 0.62 were classified as moderate and 0.21 were classified as heavy. Notice how all 3 of these add up to 1. Anytime you have a set of branches, you want it to add up to 1. So like I want these 2 branches to add up to 1 because that tells me that that's 100% of the light users classified as either this one or this one. Okay, so then I look at this and it says of the light users, 74% responded with grades that are good. So this branch right here is 0.74. This branch right here then would be 0.26. Of the moderate users, 68%. So the good grades here is 0.68, which means the not so good grades would be 0.32. And here for heavy, my good grades would be 0.52, which means my not so good grades would be 0.48. Okay, now if I think about that multiplication rule, okay, if I want the probability that A and B occur, that's the probability of A times the probability of B given A, I can just follow my branches and multiply. The probability that they are a light user and they had good grades would be the probability that they are a light user, 0.17, times the probability that they got good grades given that they were a light user. So I just follow this trail. Okay, so if I multiply these and I get 0.1258, that's the probability that they are a light user and they made good grades. So I can keep multiplying down. 0.0442. I can find all of these. 0.4216. 0.1984. 0.1092. And 0.1008. And interestingly enough, if I add all of these up, I should get 1 because these are all of my total options for this sample space. And I know if I add all of these up, I'm going to get 1. So then, if I want the probability that they describe their grades as good, that is all of these, any probability where they describe their grades as good. So that's the probability. Okay, the probability that they describe their grades as good is the probability that they are light and describe their grades as good, or, okay, and remember I can do the U sign for the or, the probability that they're moderate users and they describe their grades as good, or the probability that they are a heavy user and they describe their grades as good. And I know that anytime I see an or, I can replace it with a addition if they are mutually exclusive. And in this case, they are. One person is not going to describe themselves as a light user, a moderate user, and a heavy user. Only one of those. So basically, I just add these 3 probabilities. And I get 0.6566. So about 66% of students describe their grades as good, because I want to make sure that I do a conclusion and I actually answer the question. So, and I want to make sure I say about 66% of students describe their grades as good. Let's look at this table from earlier about allergies. I want to draw a tree diagram that does the same thing that my two-way table did. And that's fine. I can describe things using the two-way table and or a tree diagram, but I want to think about it in a given way. I could either pick allergies or female to go first. And in this case, let's make this chance process be that I picked 2 students. Okay, so I need to change my problem up. Earlier it was just picking 1 student, but since tree diagrams work best for a sequential process, let's say we pick 2 students, one right after the other, at random. And if I'm picking 2 students at random, okay, I want to know the probability. Well, in this case, I just want to make the tree diagram. So I'm going to say, here we go at the beginning, where I'm randomly selecting a student. And in this case, we are going to do the probability that they both have allergies. Because I do need to know that I'm working with allergies and not with gender. Okay, I want the probability that they both have allergies. So I'm going to randomly select a student. This is my first student. Okay. This is the probability that they have allergies. This is the probability they don't. A student who has allergies would be 18 out of 40, which means that the probability that they did not have allergies would have to be 22 out of 40. Okay, from here, for each of these, I have two options for my second student. They can either have allergies or they could not have allergies. And in this case, if they have allergies, I've already picked one student who has allergies, so there's one less to pick from and there's one less total student. And here, no allergies, there's not one less total student. There are still 22 students who don't have allergies, but there are only 39 to pick from. Same thing down here. If I picked a student who has allergies the first time, they can either have allergies or not have allergies. So if they have allergies the second time, I'm still short a student overall, but I still have 18 allergy students to choose from. But if I chose one that does not have allergies, I only have 21 of those to choose from out of 39 total students. So notice that how my number went down because I'm picking two students at random and not replacing it, so I can't pick the same student twice. That right there tells me that this is not an independent process because my overall number is going down as well. So I want this probability that both suffer from allergies, the probability of allergies and allergies. I just follow the trail. 18 out of 40 times 17 out of 39, which is 0.196. Okay, let's look at one more example. About 55% of students, high school students, participate in the school athletic team at some level, and about 5 of those go on to play a college team. What percent of high school students play a sport in high school and go on to play in college? So again, in high school, I can make a tree diagram because this is a sequential kind of event. In high school, they either play or they don't play. I'm going to let P represent play in high school, and N represent did not play. And then from there, they go on to college. And really and truly, I don't have to say that this is high school because they either play or they don't play here too. They play or they don't play. And if they didn't play in high school, we're not really worried about that at the moment, but same option. They either play or they don't play. So we have about 55% here played high school sports, which means 0.45 here. We have no information about this, so we're just going to leave this blank. And I know that 5% of these, which means there are about 95% that don't. So if I want to know what percent play a sport in high school and go on to play in the NCAA, that's this branch right here, which means I would say 0.55 times 0.05, and I would get about 0.0275. So I would say only about 3% of college athletes, of high school athletes, only about 3% of high school athletes will play a sport in both high school and the NCAA. Okay, so let's do the check your understanding. It's on page 321. The first one is about constructing a tree diagram. So I have my computers. There were 3 options for their factories: California, Texas, New York. And in each of those, there were either laptops or desktops. So when I plug in here, this was 0.4, 0.25, 0.35, and then here 0.75, which means it's 0.25, 0.7, 0.3, 0.5, 0.5, and so I would multiply all of these. That would give me a 0.3, 0.1, 0.175, 0.075, 0.175, 0.175. Add these all up. Should get 1. And I want the probability that they are a laptop, or that the computer manufactured is a laptop. So I need to find all of the branches that involve a laptop. I would add them up, because basically that's saying what's the probability that it was a laptop and made in California, or laptop and made in Texas, or laptop and made in New York. And since one laptop can't be made in 2 places, then those are mutually exclusive, so the ors just mean add. So I add them all up, and I get 0.65.